I have uploaded your grades in the class, and I also scanned your papers, graded papers, and I will just send them by email to you, so you can just have a look and see which grades you got from which question, and if there's any question that I missed to grade, just let me know. Any questions? Now today we will be, what we have been doing is just trying to solve certain Schrödinger equations. We had seen operator methods, we had seen the series expansion method for the harmonic oscillator, and we had studied to some extent the WKB approximation. Today we will be defining what's called the propagator. Now, what the basic idea is, we had already seen that if we have any ket at the time t equal to t0 is given by this state, at the time t, this ket evolves, we can obtain this evolved ket in the form e to power minus I over h bar, h t minus t0, alpha t0. Just we have this operator over here that is acting on our ket. And if we write the wave function at the time t, this is our e to power minus I over h bar, h t minus t0, alpha t0. Now, of course, this in general will not be easy to solve. That exponential operator we won't be able to evaluate explicitly most of the time. So let's just try to convert that to some integral expressions that involve just functions, which we might be able to evaluate either through some differential equation or by some other means. So I will just insert the identity over here. We know that if we are using the position kets, this is just the identity operator. So position ket is position operator is a Hermitian operator. So its eigenkets form a complete set, which basically means that we can write the identity operator as a sum over all the possible position kets in this form. And hence, this matrix, the left-hand side, is nothing but our wave function of this state alpha at its value at the position r at the time t. This is equal to d cubed r prime, r minus I over h bar, h t minus t0, r prime alpha t0. Or we can write this in a slightly different form. This is nothing but that expression, that factor at the end is nothing but our wave function at the time t0. So this psi alpha r of t, our wave function at an arbitrary time, we can write it as an integral so the time evolution of any ket, and hence, in fact, all the properties of our states are incorporated in this function over here, which is usually written as k r prime t. No, this is r, sorry. R prime t0. So it tells us how my ket evolves in time, how my wave function evolves in time. Now we can find various expressions of this. T0, which we define in our Bryan-Ket notation as R minus I over H bar, H T minus T0, R prime. Well, I can use again, a resolution of identity in terms of energy eigenstates. So let me just insert the energy eigenstates over here. So this just becomes sum over all my energy eigenstates, or let me just put A. Now keep in mind that I'm not changing the positions of neither my operators nor the kets. I'm paying attention to their positions. I don't write this operator to the, let's say, the right-hand side. I cannot do that. But what I can do now is that the Hamiltonian acting on these kets A here just gives me the energy. I over h bar EA t minus t0. Now that exponential over here, there is no longer an operator, it's just a number. So that number I can just put wherever I want. A e to the power minus I over h bar EA t minus t0. But keep in mind, this is nothing but the wave function of the energy eigenket. So we can just write it at UA R. And this is just, if you take its complex conjugate, it's again the wave function of the energy eigenket A. So that just is UA of R prime complex conjugate. So if we know the eigenkets and eigenvalues of our Hamiltonian, we can write this evolution operator. Well, in a sense, it describes the evolution of our wave function in time. So we can write that kernel, so to speak, as a sum over energy eigenkets, energy eigenstates. So this is just one of the expressions. Now let's do an example of this. We can look at the free particle. Now, in the case of the free particle, we had already evaluated the energy eigenstates, the wave function of energy eigenstates. They were just plane waves. These are my energy eigenkets with the corresponding energy eigenvalue, p squared over 2m. So these we had already obtained. Now we know the expression of our kernel, evolution kernel. Now of course it's no longer a sum because the energy eigenvalues are no longer discrete. So we have to replace it with an integral. dqp e to the power I p p dot r minus r prime over 2 pi h bar cubed. This is just UA of r multiplied by UF of r prime star. And now we have this e to the power minus I over h bar. The EA is just p squared over 2m times t minus t prime. Now this integral is kind of problematic because it's highly oscillatory, it doesn't really converge. But we have tricks to make it convergent. So let me just rewrite it in a slightly different form. dqp e to the power I p I just insert a very small positive number over there. And then eventually take the limit as epsilon goes to 0. In such a way that if p squared goes to infinity, we are evaluating all of the momentum space, including the over momenta which have an infinite magnitude. If you look at our original expression, well, they are highly oscillating terms. They oscillate infinitely fast. So there is no way to evaluate that integral. But now, since I have inserted this epsilon, the contribution of those terms will be negligible. As e to power minus some very small number times a very huge number, that will be e to power minus a huge number. So it will just go to 0. And eventually, when I take the limit as epsilon goes to 0, I obtain the required result. Now, do you know how to evaluate these integrals? Here, basically, I have an integral of this form, e to power minus alpha p squared minus beta dot p. So do you know how to calculate these integrals? Well, there are basically a couple of ways you can do. One of them, I can just write this as dpx e to power. Well, let me just skip that for the time being. What I will be using is just the result of the Gaussian integral. Basically, it tells me that if you evaluate any variable, e to power minus alpha y squared from minus infinity to infinity, well, this is a one-dimensional integral. This is just square root of pi over alpha. If you have a three-dimensional integral of this form, now this is equal to dpx from minus infinity to infinity, e to power minus alpha px squared, dpy from minus infinity to infinity, e to power minus alpha py squared, integral from minus infinity to infinity, dpz, e to power minus alpha pz squared. So although it's a three-dimensional integral, I can just write it as the product of three one-dimensional integrals. Each one of them will just give me pi over square root of alpha. I have three of them. So this expression is just pi over alpha square root, but I have three of them, 3/2. Now, of course, I also have that beta term, which will make my life a bit more complicated. Let's look at that integral. P squared minus beta p. This is equal to the integral of the exponential of minus alpha p squared plus beta over alpha dot p. Now I will just add a term here, which is beta squared, or beta over 2 alpha squared. And then I need to subtract that term. I don't want to change my expression, so I should plus beta squared over 4 alpha. I'm just completing it to squares. That's what I will be doing. The two terms that I added, they just cancel each other, so I didn't really change my integral. This is equal to d cubed p exponential of minus alpha. Well, the reason why I added and subtracted that term is that now the first parenthesis is nothing but p plus beta over 2 alpha squared. And then I have the other term, beta squared over 4 alpha. Now you see that beta squared over 4 alpha is independent of p. So I can just take it out of my integration. e to the power beta squared over 4 alpha d cubed p exponential of minus alpha p plus beta over 2 alpha squared. Okay, there's just one more step left. I will just define a new vector k to be p plus beta over 2 alpha. I'm just changing my variables. Instead of p, I'm just integrating over this k. So this is e to the power beta squared over 4 alpha d cubed k e to the power minus alpha k squared. But now I already know the result of that integral. 4 alpha pi over alpha to the power 3 halves. So basically my final result is that the integral, the three-dimensional integral of e to the power minus alpha p squared minus beta dot p is just e to the power beta squared over 4 alpha pi over alpha to the power 3 halves. This is my final result. Now what I was trying to evaluate was this term over here. Now this is what I'm trying to evaluate, that p integral. Now you see, alpha is this one. All of this expression is my alpha. And my beta is just, beta vector is minus I r minus r prime. So this k r t r prime t0 is equal to, well, I have this 1 over 2 pi h bar cube times e to the power, well, beta squared is minus r minus r prime squared over 4 alpha, minus because of that I in front of beta. And alpha is, now let me write it. This is exponential of minus r prime squared divided by 4 alpha is I over 2m h bar t minus t0. I already set the limit epsilon goes to 0 plus, now times pi over alpha or pi over I over 2m h bar t minus t0 to the power 3 halves. So this is my kind of final result. Now let me just slightly simplify it. This is 1 pi to the power, well, okay, let me 1 over 2 pi h bar cube times 2 pi h bar to the power 3 halves m to the power 3 halves minus I over t minus t0 to the power 3 halves times exponential of I m h bar over 2 r minus r prime squared divided by t minus t0. Well, this will simplify some of the terms, so k r prime RT R prime T0, this is equal to minus I M over 2 pi H bar T minus T0 raised to the power 3/2 exponential of I M H bar over 2 R minus R prime squared divided by T minus T0. So basically, given any initial wave packet, you can just use this expression to evaluate its time evolution. Let us look at certain limits of this expression. Well, you see, whenever you see such an expression, the t equal to t0 limit seems to be a bit problematic. So let's see what can we say about that limit. Now, any questions up to this point? Well, it's kind of some mathematical algebra, nothing more really. Now let's try to understand what this function actually is. Okay, we can evaluate it in some simple cases, but how can we interpret this function? Now let's first look at the limit when t goes to 0. T goes to t0. Well, let me just check the case r is not equal to r prime first. Well, let's see. I have that prefactor. As t goes to t0, that prefactor just diverges. Okay, which is not that nice. But let's look at the exponential term. The exponential is also e to power some I, so it's an oscillatory function. But what multiplies I is just divergent. So it's also a divergent expression. But that's an exponential, a phase. That is basically a phase that is oscillating infinitely fast. So that is basically 0. It will not contribute in any integral. Although the prefactor is infinite, I won't receive any contributions to any integral in this limit x from the points r is not equal to r prime. You see, eventually this k I will be using in this integral. This is where I will be using it. Now, if t goes to t0, in k I have that infinitely fast oscillating term. So very nearby values of r prime, although psi of r prime doesn't change, since I'm just considering two nearby values of r prime. Psi of psi has the same value, more or less, at these two very nearby points. But these very nearby points, they are oscillating very fast, so one will contribute to this integral with a plus sign, let's say, the other one will contribute with a minus sign. So I won't get any contribution because of that infinitely fast oscillating term. So effectively, as t goes to t0 and r is different than r prime, my k is basically 0. In the sense that it will not contribute to any such integral. Now let us look at the other case, limit as t goes to t0, but this time r is equal to r prime. Well, this time that exponential is just 0. I get my limit as t goes to t0 of minus I m over 2 pi h bar t minus t0 to the power 3/2, but this diverges as t goes to t0. So whatever this k is in the limit t goes to t0, it is 0 if r is different than r prime, and it is infinite if r is equal to r prime. So does it remind you of any function that you know? It's just a Dirac delta function. Of course, to prove that it is the Dirac delta function, there is one more thing we have to evaluate. Let's just evaluate this integral. In the limit as t goes to t0. If this is a Dirac delta function, then it should be just 1. If it is not 1, it just gives us the overall prefactor to the Dirac delta function. So let's see. This is d cubed r prime. At the top, I have my k minus I m over 2 pi h bar t minus t0 to the power 3 halves, the exponential of I m h bar over 2 r minus r prime squared divided by t minus t0. Well, let me just make a change of variable. Let me just call r minus r prime as y. So this is just d cubed r prime minus I m over 2 pi h bar t minus t0 to the power 3 halves exponential of I m h bar over 2 1 over t minus t0 times y squared. Well, this is just like my Gaussian integral that I had evaluated before. This time beta is just 0. This is equal to minus I m over 2 pi h bar t minus t0 to the power 3 halves. Beta is 0, so I don't have any e to the power beta squared over 4 pi terms. And what I have left is pi over, well, alpha is minus I m h bar over 2, 1 over t minus t0. To the power 3 halves. Well, minus i's cancel, m's cancel, the pi's cancel, this 2 cancels this 2 over here, t minus t0s, they just cancel each other. Apparently I made a mistake before, so this is 1 over h bar cubed. Well, you see, the important thing is it is independent of t. So it is equal to 1 over h bar cubed even when I take the limit t goes to 0, t goes to t0. Well, let me just correct my previous mistake somewhere. So here I have my 2 pi h bar, so this is just 2 pi h bar to the 3 halves. Okay, so no mistake over there. Okay, let me just not waste more time over here. Well, this should have been 1. I had missed some factors of h bar somewhere in the calculation. But with our current expressions, what we had shown is limit as t goes to t0 of this function. This is equal to 1 over h bar cubed, the Dirac delta of r minus r prime. Now, the reason why I'm saying that that 1 over h bar squared should not be there, well, this is an explicit demonstration for the free particle that in that limit it becomes a Dirac delta. It doesn't mean that it should be a Dirac delta for every particle, but we can generalize it. You see, we had seen that k of r prime t0, this was nothing but r e to power minus I over h bar h t minus t0 r prime. This is how we define it for any system. Now we can take the limit as t goes to t0 of k r t r prime t0. This is equal to r prime. Now t minus t0 just becomes 1. But by definition, this is just the Dirac delta function. Now, as I said, I probably missed some factors of h bar somewhere in the derivation. So that's why I'm just kind of skipping it. But keep in mind that that 1 over h bar cubed should not be there. Now, what else do we know about this function? K r t r prime t0. By definition, it was r e to power minus I over h bar h t minus t0. R prime. Let me take its time derivative with respect to t. R minus I over h bar h t minus t0. e to power minus I over h bar h t minus t0 r prime, or I h bar del k by del t is equal to, I will just write it as hk. Okay, just keep one thing in mind. This h over here is an abstract operator, where p is the p momentum operator. That's it. It's not the derivative operator in this line. Well, let me write it in this form. H is a function of r and p. Here I have the h as a function of the position r and h bar over I, the gradient. Because we had already seen that the momentum operator in position space, I can write it as the gradient operator. So K satisfies the Schrödinger, time-dependent Schrödinger equation. And with an initial value, initial wave function that is a Dirac delta. So if you want to give K a physical interpretation, it's nothing but the wave function at the time t of a particle that was localized at the point r prime at the time t0. So initially we had this Dirac delta function and we let it evolve in time. The wave function at the time t is given by this k. That is one interpretation we have of k. Questions? Yeah, we will come to that. Let's look at k again. Well, I can just separate the t and the t0 in the exponent. So what is this ket on the right, do you remember? Well, if it was e to the power minus I over h bar h t0, it would have been just the time evolution of the ket r prime. But it's not minus, it's plus. But nevertheless, this is in the Heisenberg picture. It is the position eigenket at the time t0. You see, if you remember in the Heisenberg picture, the kets didn't evolve. The kets describing the state of my system, they didn't evolve. But if you wanted to talk about the eigenkets of the operators, well, since the operators are changing in time, their eigenkets are also changing in time. So this is the eigenket in the Heisenberg picture of the position operator at the time t0. Whereas the left-hand factor is just the eigenbra of the position operator at the time t. Well, this you can say that this is the probability amplitude that a particle starts at the point r prime at the time t0 and it goes to the point r at the time t. Now, either you can just consider it through this expression of the eigenkets of the position operator in the Heisenberg picture, or in fact, if you just look at this initial definition of k, r prime describes a particle that is localized at the point r prime, and then at the time t0, then it evolves until the time t, and we are looking at the amplitude that we will be observing it at the position r. So in a sense, it's also the amplitude that the particle will propagate from the point r prime to the point r in a time t minus t0. In that sense, this is called the propagator. It just gives this amplitude that you start from here at a given time t0, the amplitude that it will be reaching this point at a later time t. Now let's just look at certain other properties of this K. Now let me consider certain integrals. Or let me look at this one. This is r e to power minus I over h bar, h of t minus t1, e to power minus I over h bar, h of t1 minus t0, r prime. I just divided my exponential into two. Since Hamiltonian, at least in this problem, the Hamiltonian I'm considering is a Hamiltonian that doesn't depend on time, so it commutes with itself at every time. So I can just treat it as if it was just an ordinary function in terms of multiplying exponentials, etc. But if I write it in this form, I can just insert an identity over there. And the identity that I will be inserting, let me just call it R1, R1, R1. This is equal to d cubed R1, r e to power minus I over h bar, h of t minus t1, R1, R1, e to power minus I over h bar, h of t1 minus t0, R0. But each of these factors inside the integral is just k. So k of r, t, r prime t0, this is equal to d cubed r1, k, r, t, r1, t1, k of r1, t1, r0, t0. Well, this kind of makes sense because I mean, we had already seen when we were discussing the fundamental concepts that the amplitude that the amplitude for A and C happening, well, that C happened, well, okay, so if you remember when we were discussing these fundamental concepts, this amplitude A, B, we said that this was equal to A, C, C, B. So you start from the ket A, the amplitude that it will eventually be the ket B is given as the A being C, and then C become the amplitude that C just becomes B. So in a different way, you can just interpret this as you start from A and reach B. If you remember, we were discussing about the Sturm-Gerlach experiments. And in between, any possible outcome of C is possible. You just sum over all possible outcomes, and A just can become a B through any one of these intermediate C states. We had, if you remember, we had these 3 Sturm-Gerlach experiments. This will be So the idea was if an outcome can happen through various intermediate states, then unless you measure the intermediate states, you just sum the amplitudes. So this was basically this equation over here, and basically we have the same thing over here in our K. So you see we had said that the K, R, T, R prime, T0 is the amplitude that a particle initially at the point R prime at the time T0 will be found at the point R at the time T. You just pick an intermediate time T1. So the particle will start at R prime at the time T0. At the time T1, it might be at the point R1. We are not measuring it. And then if it's at the point R1 at the time T1, it will have a finite amplitude to propagate to the point R at the time T. The total amplitude is just the product of these two amplitudes that you start from R0, go to R1, and from R1 you go to your final destination R. But since you are not measuring what R1 values are, you need to sum up over all the possible values of R1. So it is just this expression over here. So basically, if this is, let's say, your R, this is your R prime, this is at T0, this is at T1. You just pick up some intermediate time. Now this is T. This is our T1, our intermediate time. My particle starts here. Then it can, at the time T1, it can be at this point. So I should talk about the amplitude that it will move to this point, and then from this point it can move to R. Or I start from R prime at the time T1, it can just reach this point, and then from that point it propagates to R. It starts from here at the time T1, it is right over there, and then at the time T, it just reached my final point R. The total amplitude that it will go from R prime at the time T0 to R at the time T is just the sum of all these amplitudes. Now let me just mention one more property of this K, and then we can give a break, after which we will just come back to this property. And you see, the idea is nobody tells us that we should choose just one interval T1. We can choose many time intervals between T0 and T. And just sum of all the amplitudes. And then it will just become what's called the path integral. So that's where we will be heading. But before you go for a break, let's just look at another property of K. K of R, T, R prime, T0. This is equal to, this was how we had defined it. Or e to power minus I over h bar, EA, T minus T0, A R prime. A being a complete set of energy eigenkets. Now let me just take R and R prime to be equal. And then integrate over R. This sum is over A e to power minus I over h bar, EA of T minus T0. Well, just to see it a bit more clearly, I will just change the order of those two factors. But you see, that integral over R is nothing but the identity operator between the bra A and the ket A. So that integral is nothing but AA, which by definition is 1. So d cubed R, K, R, T, or T0 is equal to A e to power minus I over H bar EA of T minus T0. Now let me make a change of variable. Let me just define beta to be I over H bar T minus T0. Then d cubed r K just becomes sum over all the energy eigenstates of e to power minus beta EA. Well, this is nothing but the statistical partition function. So basically, whatever you do in quantum mechanics, just using this similarity, let's say, you can also use in statistical physics. If you can determine K, you know the partition function. If you have, we will be describing many approximation methods. If you know K, if you can calculate K within these approximations, well, you know the partition function of the system. Let us just do one more thing. This we had already seen that this is in sum of all the energy eigenstates. Now let me integrate this over time. From T0 up to infinity. This is sum over A. Well, let me just, for simplicity, just set T0 is equal to 0. It will just simplify my treatment. Will not really change much. This is T minus T0. Sum over A, integral from 0 to infinity dt e to the power I e T minus, no, E minus EA times T. Well, again, I will just make one trick. Instead of taking E to be real, I will just assume it's slightly imaginary. The reason why I add that I epsilon is so that my integrand just goes to 0 as t goes to infinity. Otherwise, I end up having this infinitely oscillatory contributions, which are not well defined. And then I will take the limit as epsilon goes to 0. But that integral I can evaluate, and that integral is nothing but 1 over I e minus EA. So basically what I do, I take my K, set the two positions to be equal, R is equal to R prime. Well, T0 is 0, I can just choose my 0 time to be any time. And integrate over the positions, and then take a Fourier, kind of a Fourier transform over the time by multiplying it with this factor e to the power I e t, integrating over t from 0 to infinity. I obtain some other function, which is nothing but the sum over all the eigenstates of 1 over the E minus EA. This is my new function. Let me just call it G. But you see, this function has poles whenever the energy is equal to one of the energy eigenstates. So we didn't solve the, okay, in this problem at least, in the simple example of the free particle, what we did was we first solved the time-independent Schrödinger equation to obtain the energy eigenkets. And then from those energy eigenkets, we obtained the K, which was kind of, we already know the energy eigenkets, energy eigenvalues. But now this tells me that if you can calculate K by some other means, not necessarily by solving the time-independent Schrödinger equation, but by some other means, if you can obtain K, you can find the spectrum from the K also. Just through this procedure, set the positions to be equal, integrate over the positions, and integrate over time. And in fact, integration over the positions is not really necessary. I mean, if you just repeat the same procedure from t0 up to infinity, from 0 to infinity, e to power I e t, k of r t r prime t0, this is actually sum over a minus I u a of r prime divided by, now this is star, e minus ea. Just repeat the same procedure. So you see, this function, this time integral of k, has poles at the positions of my energy eigenvalues. So if I evaluate it, find the position of the poles, then the residues at those poles are nothing but my wave functions. Let's say just fix r prime to be some constant. So ua star of r prime is just some constant. Its r dependence just gives me the energy eigenvalue ua of r. And you can just properly, if you normalize it, you know the energy eigenstates. So this is an alternative way of solving the Schrödinger equation, assuming you'll find a way to determine k. Any questions? Now, just to sum up what we had done. Basically, first we had shown that there is this function k, so-called the kernel, which allows us to determine the wave function at any time, starting from the initial value of the wave function. So this was kind of one of the purposes we were looking at this k. So it allowed us to determine the time evolution of any wave function, any initial state. But this was a simple example where we determined this k for the free particle. But then we said that, okay, we define this, so what does it correspond to? We had seen that it's actually the solution of the time-dependent Schrödinger equation with an initial value, initial wave function, just Dirac delta. Okay, there's a problem of factors over there which we should fix. And then we were just looking at some properties of this function. And we were discussing, one is this property. So once you interpret it in terms of the propagator or the amplitude that it moves from point A to point B in a given time, then this property is just kind of obvious. The amplitude that it goes from point A to point B is nothing but the amplitude for it to go from point A to point C and then from point C to point B. You multiply them. Well, the point C can have any value. So to obtain the total amplitude, you have to sum over all the amplitudes. So this is just that statement. And then we were looking at some other uses of this K. One of it is just set the positions to be equal and integrate over the positions. And if you just assume that T is not the time but some imaginary parameter and relate it to beta. Well, in statistical physics, by the way, beta is nothing but 1 over Boltzmann constant times the temperature. So from this K, we obtain the partition function. And if you integrate over time by multiplying with this e to power I e of t, you get a function which has just simple poles at the positions of the energy spectrum. So you can basically determine all the energy spectrum once you know K. And the residues at those positions just tell me what the wave functions are corresponding to those energy eigenstates. So basically K contains all the information that we might be interested in. It contains the information about the wave functions, it contains the information about the energy eigenvalues, etc. We can use it in statistical physics. But the question is, how do we calculate K? One way is solving the Schrödinger equation, but kind of if we are to solve the Schrödinger equation, what's the purpose in K? I mean, all the information contained in K we can also obtain by solving the Schrödinger equation. But there are alternative ways of determining what K is without actually solving the Schrödinger equations. And one of those is what we call the path integral. And that is what we will start after the break. Any questions?
Propagator'ın zaman integrali bizim için yani wave function'ın mesela atıyorum her A'ya eşit olduğunda rezidüler verilecek ya bize olabilecek. Onların aslında enerji eigenketlerine ya da onların olduğu yere göre toplamı bizim için orada yaşayan wave function'lara mı veriyor kısaca yani. Yani şunu söylemek istiyorum. Sonuçta propagator bize işte hangi wave function'lara ulaşacağımızı söyleyecek belli zamanlarda. Onların en kötülüklerini verecek. İşte denklemin sağ tarafından da orada yaşayan wave function'lar üzerinde bir toplam mı yapıyoruz fiziki anlamda?
So, what do you mean by wave functions living there?
Mesela atıyorum A'ya eşit olduğu durumlarda bir pol var. Demek ki orada bir wave function mı var demek istiyoruz aslında fiziken. Yani denklemin sağ tarafını sol tarafıyla ilişkilendiremedim açıkçası.
So what we are saying is that, yeah, you see, okay, one thing is this is an identity in the sense that the left-hand side should be equal to the right-hand side, which tells me that the left-hand side should have simple poles, assuming I have discrete energy eigenvalues, mathematically speaking. So if the left-hand side has distinct poles, then I can, simple poles, then I can talk about the residues at those poles, and the residues at those poles just tell me what the wave function are.
Zaten belirli bir time sonrasına bakıyorsan time evolution creation da var. K benim için zaten herhangi bir wave function oluyor.
True.
Neden ona ait bir şeymiş gibi davranıyorsun?
Well, the thing is, the problem is, can you solve the Schrödinger equation? So if you can solve the Schrödinger equation, then we already know K. But if I can solve the Schrödinger equation, I already have all the information that I want from K. But the problem is, what if I cannot solve the Schrödinger equation? Or can I obtain K by methods that don't involve solving the Schrödinger equation? Then we are saying that, okay, K contains all the information that we can look for, but how do we extract those information? If we calculate K by some other means, not by solving the Schrödinger equation. Well, you're right in a sense. If we are to solve the Schrödinger equation, K doesn't really have too much of a significance. So, I mean, if we know the solutions, we know the solutions, we know everything that we can extract from K. But what if there is no Schrödinger equation that we can write? Or what if we cannot solve the Schrödinger equation? So this will allow us to obtain some other approximation methods for the energy eigenvalues and energy wave functions. One thing.
Aslında şimdi tahmin ediyorum sadece gelecek derste ne yapacağımızı çözülemeyen potansiyeller için o zaman bir distinction mi yaratacağız başka bir
Aynen.
konu için?
Well, you see, path integrals, for example, is used mainly now with computers. Because we will see that, we will discuss it next hour. Let me not delve too much into it yet. So see you after 10 minutes.